Hi everyone, this is Adam. So today I'm going to start arguably my favourite chapter. One of my favourite chapters anyways. It's calculus. Okay, so calculus is basically the study of rates of change. So basically it's differentiation is the first part of it. Integration is basically the opposite of differentiation, but we're just going to do differentiation for now. Okay, so there's two chapters on differentiation, and then there's one on integration. Okay, so basically a derivative of a function, you're basically just saying the slope of it. Okay, so for something like y equals mx plus c, the derivative of this is equal to m. Why? Because m is a slope. So if you remember from third year, this is the y-intercept, and then this is the slope. So the derivative is just equal to m. Okay? Now, the problem is that what if I said y equals, say, x squared? Well, now that's not the same. Okay? Now all of a sudden you're saying, oh, well, hold on. Now it's squared. So I actually don't know what the slope is. And also the slope is constantly changing. Because if I look at it, sorry, I don't know why I drew this so long. If you draw it like this, the slope here is different to the slope here. So in the top one, we have that it's just a constant, that the slope is always the same. So if I look at this point, I just have a constant slope. If I look at this point, I have a constant slope. Now derivatives, it's basically how do I find the slope of a function that isn't just straight, where the slope is constantly changing? How can I get a formula for the slope? Okay, so I'm going to start from very basics. All right. Okay, so this is called differentiation from first principles. You can be asked to do this in an exam. If you get decent at it, it's a very easy question. Okay, but you have to, get into the thick of things. Okay, so basically, in this case, if we have some function f of x and we plotted it, and it looks something like this, say. Let's say we want to figure out what is the slope at this point. Okay, so again, I'm just going to do the basic idea of what I want to do. Okay, so let's say this is an x value of x. This is at a height of f of x. Now, what I want to do is so again, I'm using the slope. What is the slope? So slope is just rise over run. So m is just rise over run. Okay, so I need to pick 2 points, say that point and this point. Now remember, I want the slope specifically at this point. Okay, but let's say I pick 2 points for the minute and try and get the slope of them. Okay, so say this is x plus h. So h is just the distance that I'm going to the right. Okay, the height then is just going to be f of x plus h. So this point here is just f evaluated at x. This point here is just f evaluated at x plus h. Okay, so now if I get the slope between these 2 points, so first of all, what is the slope that I want to figure out? I want to know what is this slope right there. So that's the slope that I'm actually looking for. Now, what slope am I actually calculating? I'm calculating this slope from there to there. Okay, now again, this might be really stupid at the minute, but just give me about 5 minutes and I'll be able to explain why I'm doing this. So first of all, if I calculate the slope of the pink line, what is it? So it's the rise over run. So m is just equal to rise over run. What's the rise? So we can do this. The rise, so what's this distance? This is just f of x plus h minus f of x divided by the run. What's the run? What's this distance here? H. So it's just h. Okay, so the slope is just this. Great. The problem is that the slope of this pink line is not the same as the slope of the red line down here. But if I were to, instead of picking this blue point up here, if I made h smaller and picked, say, this point here, and then got the slope, like this. See the way the slope of this kind of teal line, maybe, I'm not really sure, but this colored line is much closer to the slope of the red line. So if I make h smaller, then I get closer to the red slope. Okay? And you can probably imagine that if I start here, if I keep bringing h smaller and smaller and smaller and smaller, and I keep going left and 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 left, and I get really, really close, then I'm basically going to have the correct slope. Okay? So hopefully that makes sense. Hopefully, if I take h as being quite big, then my slope is quite off. If I make it smaller, it gets better. And therefore, if I make it really, really small, then I should get a very good approximation. Okay? So now, this is where I'm going to start using limits. So I want h to be as small as it can be. Okay? So the slope of this function, m, is going to be equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So now, again, maybe some of you didn't watch the chapter on limits, but basically, all you need to know is a limit. I'm not saying h is 0. I'm saying that h is so small that it's basically 0. Okay? So in the limit as h goes to 0, what this is saying, what does this thing look like as h gets really, really, really small? So if you plug in h equals 1, you might get some number. If you plug in h equals 0.1, you might get a different number, 0.001, 0.0001, 0.000, load of zeros. You would eventually approach a certain value. Okay? So you're saying that if h is absolutely tiny, what number do I end up with? Okay? Now, I'll do a couple of examples in a second, but this is what it is, okay? Another thing that I want to say is that the slope, m, we always write as df dx dy dx y prime or f prime, okay? So this is just notation. Okay, so that's all. Typically, it'll be this one that you're showing. But basically, where this comes from, the df basically means an infinitesimal part of f divided by an infinitesimal part of x. So it's just slope is equal to rise over run. So a small change in f is just a small rise. A small change in x is just the run. So it's just the rise over the run. So this is how it's written, okay? Or as f prime or y prime, just as shorthand notation, okay? Just to make your life a little bit easier. Okay, so now, if I said y equals 3x plus 7, or f of x equals 3x plus 7, and I asked you, what is f prime? We're going to use this formula up here, okay? So, it's equal to the limit. Now, first of all, you can tell me what the slope of this is straight away. Does anyone know what it is? Again, you can pause the video and think about it. It's 3. Remember, if it's a straight line, this is always a slope. Okay? So, that's what I should get. So if what I've done up here is correct, and this does make sense, then I have to get 3. And if I don't get 3, then I know I'm incorrect. All right? So, the limit as h goes to 0 of f of x plus h. So basically, wherever you see an x, you just replace it with an x plus h. So it's going to be 3x plus h plus 7 minus f of x, which is just 3x plus 7, all divided by h. Limit as h goes to 0 of, this is going to be 3x plus 3h plus 7 minus 3x minus 7. Now, the plus 7 and the minus 7 cancel. The 3x and the minus 3x cancel. So I'm just left with 3h over h, which is equal to the limit as h goes to 0 of 3h divided by h is just 3. What's the limit as h goes to 0 of 3? Just 3. If I have 3, if you plug 3 into your calculator, and it has no dependence on h. So basically, it doesn't matter what h is. So this could be the limit as h goes to infinity as well. It doesn't matter at all. Okay, you would still get 3. Okay. All right. Now let's go back up to our other example. Y equals x squared. What is the slope of that? Because here the limit as h goes to 0 didn't really come into effect. It will now in a second. So if I said f of x equals x squared, what's df dx? So you would say, okay, it's the limit as h goes to 0 of f of x plus h. So x squared, if I plug in x plus h, I just get x plus h squared. Minus f of x, so minus x squared, all divided by h. Okay, so again, the first one, you just plug in f of x plus h. So here, it just squares. So here, it just squares as well. Minus f of x. Okay, so it's the limit as h goes to 0. If I square this out, I get x squared plus 2xh plus h squared minus x squared all over h. Okay, all fine. So I get the limit as h goes to 0 of, so now the minus x squared and the x squared cancel. 2xh divided by, I'm just left with 2xh plus h squared all over h. This is the limit as h goes to 0. 2xh divided by h is just 2x. H squared divided by h is just h. So now, the limit as h goes to 0 of this thing, so if I let h get really tiny, I'm basically just left with 2x. So this is the very important distinction, and please listen to what I'm saying. I'm not saying h is 0. I'm not saying that for a second. What I'm saying is, I'm saying that h is so small and so tiny that if I have 2x plus h, I can say, well, the plus h is going to be 0.001, 0.0001, 0.0000001. It's basically, it's so small, I can kind of just round it off, is probably the best way of saying it, okay? That h is so tiny and therefore I don't care about it. It's too small, round it off, so I just get 2x. Okay, that's what you're saying. You're saying that if I plug in smaller and smaller numbers, what number will I approach? I'll approach 0. So h will approach 0, and therefore I can just let it be 0. and therefore it's equal to 2x. So I'm not saying h is 0, I'm just saying that as it gets smaller and smaller and smaller, it will continuously approach 0 and it will look like 0, and I can get very close to 0, and therefore I can just say that it's 0. I can just round it off and just say, no, I can just leave that off. I don't really care. All right? So that's it. So remember, this 2x is equal to f of x, f prime of x, or df dx. So this is the slope of y equals x squared. So again, that's the most important thing. Remember, when you differentiate, you are getting slopes. That is the most important thing. This formula up here that we used, this is rise over run. And please do not forget that, because it's such an important formula. Like if you go back in the past papers, it's almost always just tons of differentiation and tons of integration. These are arguably the most important chapters of paper 1. Okay, it comes up loads, and they can because it's such an applicable thing. If you go to college and you're doing any engineering, any biology, anything like that, it's almost always going to have this, because these are rates of change. If you want to look at how fast is something going, how fast is something growing, how fast, did something like COVID-19, how fast did that spread? These are things you're always looking at, rates of change. Okay, so this is really, really important and really, really applicable to other things. Okay. So I'll do one more. What if f of x is equal to, say, 5x squared minus 2x plus 5? And I want to find what is the slope of this. So f prime, I can say it's the limit as h goes to 0 of 5. Again, you just plug in x plus h. Plus 5 minus 5x squared minus 2x plus 5. All over h. Okay, so now if I multiply this out, I'm going to get 5x squared plus 10xh plus 5h squared minus 2x minus 2h plus 5 minus 5x squared plus 2x minus 5. All over h. Now again, the 5x squared will cancel with the minus 5x squared. The minus 2x will cancel with the plus 2x. And the plus 5 will cancel with the minus 5. So you notice in all of these examples, this is always cancelled out to 0. Okay, and that will always happen, and if it doesn't, you've been a mistake. Okay, so this is just the limit as h goes to 0 of 10xh divided by h is just 10x. 5h squared divided by h is plus 5h. Minus 2h divided by h is just minus 2. And that's it. Okay? And again, if I let h go to 0, then I just get that this is basically 0. So I'm just left with 10x minus 2 is equal to f prime or df dx. Okay? So now, they might ask you, they might say, what is the derivative at x equals 2? And you'll say, okay, well, I have no idea what that is. You'll say, okay, well, f prime of x, this is the derivative, and it's equal to 10x minus 2. So if I want to know what is this equal to when x is 2, you simply get f prime of 2. 10 times 2 minus 2, that's equal to 18. So the derivative, or the slope, at x equals 2 is 18. Okay? So hopefully that's all okay. Now, The very, very next thing. So we've done the first principles. This is kind of the understanding of differential calculus. Now, the next thing that we do is basically you only ever have to do the first principles if you are specifically asked. But now, thankfully, we have shortcuts. So you don't have to do anything more painful, okay? Because you might have been looking at those and said, oh, that's a real pain. Do I have to do that every time? No, you don't. There are simpler ways. So the first rule is the power rule, which comes up the entire time. It is if f of x equals x to the power of n, f prime of x is equal to n x to the n minus 1. Okay? And again, I'll just do an example. Up here, we got the derivative of x squared, and we found that it was 2x. So if I apply this and say, okay, well, what if n is 2? Then I get that f of x equals x squared, and f prime of x equals, plug in 2, I get 2x to the power of 1, which is just 2x. So yeah, this is correct. So this is a very, very important rule to remember. Now again, I think this is in your log tables. I'm pretty sure it is. But guys, I please just learn it. It's just so much easier just to have it offhand. And honestly, it's one of those things of you should have so many examples done before you go into your leaving cert. This thing would just be off the top of your head straight away. Okay? Now, some of you might be a little bit vigilant and will sit there and say, well, hold on, what if n is 0? What happens if n is 0? Is the derivative just 0? Yes. So let's say f of x is equal to a constant. F of x is equal to 7. F prime of x is equal to 0. Why is that? Remember, f prime of x is df dx, which is basically small change in f divided by small change in x. If x changes a little bit, does 7 change? No. 7 always stays the same. It doesn't matter if x is 10 or if it's 20 or if it's minus 3.2, f of x is 7. So it doesn't change. And therefore, if you ask for the slope, slope is the rate of change. It's saying how fast is it changing? Well, it doesn't change. And therefore, the slope is just 0. Okay? And just remember, x to the power of 0 equals 1. Okay? So if you differentiate a constant is just something that doesn't depend on x. Okay, so like 7, 2, 10, 3, whatever. Pi minus 17.2, all these different things. They're just constants because they don't change in x. If we go back up to this example here, this isn't constant, this isn't constant, this is constant. Because it's just 5, it's plus 5. It doesn't matter what x is. You always add 5. Okay, and that's that. Okay. That's another one. And then the very last one is just f of x is equal to ax to the n. So let's say you multiply this thing by a. What happens? You can basically just ignore the a and just differentiate x to the n like normal. That's it. That's the only difference. So it's just here, if you have an a here in this one, then you just have an extra a down here. Only difference. Okay? So hopefully that's all right. So now let's do a couple of examples. So let's say f of x is just going to be 9x to the 7 plus 4x cubed. And I ask you to get f prime of x. Remember, you just ignore the 9, you bring the power down, and you divide it by x. Same thing, you basically ignore the 4 for a second, you bring down the 3, and you divide by x. So this is just simply equal to 63 x to the 6 plus 12 x squared. And that's it. Okay? Alright. Now another one, I'll do another one. If, let's say g of x is equal to root x minus root x cubed plus 1 over x squared. How do I differentiate this? Believe it or not, this is just the power rule. It's just this again. Okay? To see that, I'm going to change all of these to powers of x. Okay? Root x, that's x to the power of what? X to the power of a half. So hopefully you remember that from the indices chapter. Again, I have a video explaining the indices if you'd like to go back and look at it. Basically, root x is x to the power of a half. The cube root of x is x to the power of a third. The fourth root of x is x to the power of a quarter, on and on and on. So it's just x to the power of a half. This now is x to the power of 3 over 2. Remember, the square root is to the power of a half. So this thing is just equal to, so the square root of x cubed is just equal to x cubed all to the power of a half. When the powers are like this, you multiply them, and that's how I got 3 over 2. The very last one, that's x to the power of minus 2. So remember, the minus basically means it's 1 over that thing, okay? Because remember this thing, you can also write it as x to the power of 0 divided by x squared. Minus the powers, 0 minus 2 is minus 2. So I'm just left with this. Okay? So now g prime, differentiate. So the half comes down. So I get a half minus 1 off the power. I get to the minus half. Minus, bring the power down. It's 3 over 2. Minus 1 off the power. I get x to the power of a half. The minus 2 comes down, and then you minus 1 off the power, so I get x to the minus 3. So this is equal to 1 over 2 root x. So this is 1 over the square root of x times 1 over 2, so it's 1 over 2 root x. This is going to be 3 x to the power of a half, that's root x over 2. And the very last one is just minus 2 over x cubed. So that's the rate of change of this. Okay? All right. So hopefully that's all okay. Now the next example that I want to do is, okay, this one is an extremely important example. It comes up a good bit, and honestly, basically all my maths cream students, they just forget how to do this, okay? Because they just forget that when you differentiate, you have slope. That's what you have, okay? So, it might say, graph the function f of x equals 2x cubed plus 5x squared plus x minus 3. Again, all you have to do here is just start plugging in numbers. So first of all, if I plug in 0, I get minus 3. There's one root is here, and the other root is somewhere over here. So it's simply just like this. Like that. Okay? I have no idea where that line has come out of. This one? Yeah. Sorry, I don't know where that came out of. But anyways. And that's it. So that's f of x, roughly. Okay? And they say, okay, what's f prime of x? So differentiate. So remember, 2x cubed, the 3 comes down. 2 times 3 is 6. Minus 1 off the power, I get x squared. Plus, the 2 comes down. 2 times 5 is 10. Minus 1 off the power, I get x. X is x to the power of 1. The 1 comes down. If I different, so the 1 comes down, I get x to the power 0, that's just 1. So it's 1 times 1, so it's just 1. And then minus 3 differentiated is 0. Okay, so remember, minus 3 is a constant. And therefore, the derivative is 0 because it doesn't change. Okay, very important. Okay, so that's the slope. Then it says, hence find the slope of the tangent, okay? The slope of the tangent to f of x at 0 minus 3. So 0 minus 3 is here. And they're saying, find the slope of the tangent. The slope of the tangent is basically the slope along that line, okay? So, you know, back up here when I was drawing these lines, they're all tangents. So, sorry, no, and the red line is a tangent. So the red line is, so basically a tangent is, if I just draw quickly tangents of circles, a tangent of a circle is just anything that kind of goes along here, or here, or here. So it's kind of like just going along it. Same way if it was like a curve like this, a tangent would be here or here. So it's just like kind of going along the edge. It's kind of like if you grabbed your pencil and kind of put it along it, what line would that make? So in this case, it's like this one, okay? Again, if I wanted the tangent here, then it would be something like this. You know? And then here, it would be something like that. Okay? So that's what a tangent means. Okay? Now, it says find the slope of a tangent at this point. So now think about it. Does anyone know how we would do that? Remembering that this is equal to slope. Simply plug in 0. F prime of 0 equals 1. And therefore the slope of this tangent equals 1. And that's it. Okay? The next thing they ask is say, okay, find the equation of the tangent. So the equation of a tangent, you would say y minus, so it's just a straight line. So y minus y1 equals m into x minus x1. Remember, this is x1, y1. So it's going to be y plus 3 equals x minus 0. So it's y equals x minus 3. So hopefully that's all okay. All right. So that's it. That's all you have to do. Okay, so that's how you find the equation of tangent. Just get your function, differentiate it, figure out what x value you want. In this case, it's 0. Find the slope, and then say, okay, well, the tangent obviously goes through that point, and therefore it's just this. Okay? All right. Now the next thing is called the chain rule. Okay? So now we're getting, now this is very heavy, so this is not, honestly, this is a video that you could probably pause and just every 10 minutes and come back to like a day later, but I'm just going to keep plowing on. So the chain rule. So what is the chain rule? The chain rule is basically if you have, so again, is this formula in your log tables? Yes. If you don't have practice with this, will you be able to figure it out on the exam? No. It's very, very, very difficult, okay? It takes a lot of getting used to, and the best way of doing it, I find, is by examples. So I'll do 3 or 4 examples, and then I'll leave it at that, okay? So it says differentiate the cube root of x squared plus 4. Do f prime. Basically, what you do is, so I'm going to do it using the formula first. So I can say this is df dx, but this is equal to df du times du dx. Why are these the same thing? Because I can get rid of these du's. Okay? So these two things are the same thing. What this is saying is I can split this into two separate derivatives and then just multiply them by each other. Because if I ask you right now to differentiate this, you might say, oh, I have no idea how to do that. But hold on, if I said the cube root of x squared plus 4, well, that's just equal to x squared plus 4 to the power of a third. Now you're saying, well, hold on, that looks like something I've seen before. That looks like the power rule. Like back up here when I had the third. It looks very similar. The problem is you're probably sitting there and saying, well, if this plus 4 wasn't there, then I'd be grand. And you'd be correct. It's just that plus 4 that's a bit of a pain. Okay? So how do I navigate this? In this case, let this be equal to u. So x squared plus 4 equals u. So that's where this formula comes from. So now I have f of u is equal to u to the power of a third, and I have u is equal to x squared plus 4. Now I can use this formula up here. df du, I can simply use the power rule. I can get a third u to the minus 2 over 3. And I can get du dx. If I differentiate this with respect to x, I just simply get 2x. So remember, if I differentiate x squared, I'm just left with 2x, and if I differentiate 4, I get 0. So I'm just left with this. So now, if I multiply these two things together, I get a third times u to the minus 2 over 3. Well, that's u is just equal to x squared plus 4 to the minus 2 over 3 times 2x. Boom, you're done. Nothing more can or has to be done. You are finished. Okay? So the chain rule is basically saying, okay, well, you just replace one of these with a u. You differentiate like normal. And then whatever you pretended was u, you multiply, you find the derivative of that, and then you multiply them by each other. Okay? Now this probably comes across as very, very awkward. I've done one formula way, but now I'm just going to do things by kind of like intuition. Okay? This is just, if you do a few examples, it'll be much easier. Okay? So, I'll do a couple of examples right now. So if I want you to differentiate 7x plus 1 to b squared. The way that I do the chain rule in my head is I say, well, I don't know how to differentiate this, but I can say, well, if this was just x, how would I differentiate it? Well, the power would come down and add minus 1 off the power. Okay? So say that's f of x. This is f prime. Now, the thing is, the way I'm doing it is you can basically act a bit ditzy as if you don't know and say, oh, it's no difference, and then just differentiate it like normal. So remember, if this thing was x, I would just differentiate it like normal. The 2 would come down because it's the power rule. I'd minus 1 off the power. I'd be left with 7x to the power of 1. But now you multiply by the derivative of the thing you pretended was x. I pretended that 7x plus 1 was x, and therefore I need to differentiate that with respect to x, and I get 7. So it's simply 14 times 7x plus 1. And that's it, done. So you just pretend it's x, and then multiply by the derivative. Okay, that's the easiest way that I personally find of doing it. Okay? So another one, it could be differentiate. So g is going to be x squared plus 3x to the power of 12. Differentiate this. Again, I'm going to pretend that this thing is x. If it was x to the power of 12, what would I do? 12 would come down. I'd minus 1 off the power. Okay? And now I need to multiply by the derivative of the thing I pretended was x, which is this thing. If I differentiate that with respect to x squared, that becomes 2x. And 3x, that becomes plus 3. Boom, you're done. Nothing else has to be done. You're finished. Okay? So hopefully that comes across and makes sense. All right? Okay. I'll do a few hard ones. All right? Yeah. So what if f of x was equal to the fourth root of 6 minus root x? So remember, the very first thing you do is you always change the power. This is 6 minus root x to the power of a quarter. Okay? So again, if this was just x to the power of a quarter, what would I do? The quarter would come down, and I would minus 1 off the power. Grand. But now, remember, I need to multiply by the derivative of the thing I pretended was x. What did I pretend was x? I pretended 6 minus root x was x. Okay. This is a quarter. 6 minus root x to the power of minus 3 over 4. Multiplied by. If I take the derivative of 6, I get 0. Remember, root x is x to the power of a half. So the half would come down, so I get minus a half. And I would minus 1 off the power, I get x to the minus half. Just tidying up, I get minus 1 over 8, 6 minus root x, to the power of minus 3 over 4, to the power of x to the minus half. And that's it. Okay? Alright, so hopefully that's all okay. Alright? So yeah, I think I might leave those at that. But that's basically your chain rule. So you differentiate, you act it, say you just pretend as if it was x. And then once you differentiate, you say, okay, well, what did I pretend was x? I pretended this was x. Now I need to multiply by the derivative of that. Okay? That's my best way of personally thinking about it. Now, next thing is the product and the quotient rule. Okay? So the product rule basically says that if you have f is equal to u times v, then f prime is equal to u prime times v plus u times v prime. So basically you differentiate one first and then differentiate the other. That's it. An example of this would be f equals x squared, because that's x multiplied by x. So I can say, okay, we'll plug it into this formula. Well, f prime, well, I know from the power rule, if I bring the 2 down, I get 2x. So I should get 2x. So first of all, differentiate this, I get 1. 1 times x is x. Now if I differentiate this, I get 1, and I get x. X plus x is indeed equal to 2x. Okay? So that's just a quick example of the power rule. Okay? Sorry, of the, product rule. Now the quotient rule. The quotient rule is harder. Okay? So if f of x is equal to u over v, then f prime is equal to, it's going to be v u prime minus v prime u all over v squared. Okay? So, let's say f of x is equal to 1 over x. F prime is equal to what? So first of all, it's v. So remember, in this case, u is 1, v is x. So it's v, which is x, times u prime. If I differentiate 1, I get 0. Times v prime is going to be 1, times u, which is 1. All over v squared, so it's just x squared. So it's equal to minus 1 over x squared. And was that what I was expecting to get? Yes. Because again, f of x is equal to 1 over x, which is x to the minus 1. If I do the power rule, the minus 1 comes down. I get x to the minus 2. That's equal to minus 1 over x squared. So those two things are the same thing. Okay? So now I'll do a couple examples. So the product rule, let's say we want to differentiate this. Say f of x is equal to root x times 2x plus 4. How would we differentiate this? So remember, you differentiate the left first. So root x, that's x to the power of a half, 2x plus 4. So f prime is equal to, differentiate the left thing first, the half comes down, minus 1 half the power, like so, times 2x plus 4. Second part, you differentiate the second one, which in this case is just simply 2. Okay? So this is equal to, so the half will cancel with the 2 and the 4, so I'm just left with root x, 1 over root x, into 4 plus 2. No, sorry, geez, x plus 2. Plus 2 root x. Like that. And that's it. Okay? So again, you won't be asked to simplify these. That's simplified enough. Alright? So that's the product rule. I'll do another product rule. So let's say g of x is equal to 3x squared minus 2x plus 5 times 4x squared plus 3x minus 1. So again, differentiate this first. If I differentiate this, I'm going to get the 2 comes down, 2 times 3 is 6, minus 1 half the power, I'm left with 6. Differentiate minus 2x, I just get minus 2, because the 1 comes down and then divide, minus 1 half the power, so I get x to the power 0, which is just 1, so I'm just left with the minus 2. Differentiate 5, I get 0. So I'm just left with this, plus, now it's the first thing, times the derivative of the second thing. So if I differentiate the second thing, the 2 comes down, I get 8x plus 3. And again, that's it. No more work has to be done. Okay? Now, those are two product rule examples. Now we'll do a quotient rule example. Okay? So, if I want to get the derivative of f of x, which is 1 over x plus 3, how would I do this? So remember, u over v. So u is equal to 1, v is equal to x plus 3. So f prime is equal to, remember, it's v u prime minus v prime u all over v squared. If I do this, I get x plus 3 times the differential of 1, which is 0. The differential of x plus 3 is simply 1 times u, which is also 1. All over v squared is going to be x plus 3 squared. And this is just equal to minus 1 over x plus 3 squared. Okay. Now again, I could have also used the chain rule here. So again, there's loads of ways of doing this. Okay, you don't need to do it the same way that I'm doing. I could have also used the chain rule. I could have said, well, 1 over x plus 3, well, that's simply equal to x plus 3 to the minus 1. So again, if I just differentiate like normal, I'd say, okay, well, use the chain rule. Minus 1 comes down, minus 1 off the power, multiply it by the derivative of the thing inside. In this case, it's just 1. So I'm simply left with minus 1, x minus 3 to the minus 2. That's equal to minus 1, sorry, plus 3, over x plus 3 squared. So you get the same answer both ways. So whichever way you prefer. Okay? I'll do one more and then I think I'll leave it at that. Yeah. What if f of x is equal to, sorry, I might just move that over. F of x is equal to 3x squared minus 5x all over x squared minus 1. Remember, that's equal to u over v. So u is, in this case, is equal to 3x squared minus 5x. V is going to be x squared minus 1. So now, let's use the quotient rule. So it's going to be f prime is equal to, remember it's v, which is x squared minus 1, times u prime. Differential of the top thing, that's just 6x minus 5. Minus the differential of the bottom thing, that's going to just simply going to be 2x, times the top thing, which is 3x squared minus 5x. All divided by the bottom thing squared. I'm just going to simplify the top. So the top is going to give me 6x cubed minus 5x squared minus 6x plus 5 minus 6x cubed plus 10x squared all over x squared minus 1 squared. So this is going to be the 6x cubed and the minus 6x cubed cancel. 10x squared minus 5x squared is just 5x squared minus 6x plus 5 all over x squared minus 1 squared. Okay? Alright. So that's that, basically. Okay? So now, the very last, well, kind of coming towards the end of this, going on to trigonometric functions. So what are the derivatives of sine, cos, tan? These are just very handy to know. Okay? If f of x equals sine x, cos x, or tan x, the derivative is equal to cos x minus sine x secant squared. Which is simply 1 over cos squared x. Okay? Again, these are in your log tables. It's very, very handy to just know them. Okay? It's just a bit painful if you don't. Okay? I'll do a couple of derivatives with sines and coses. So let's say you are asked to differentiate f of x is going to be cos 4x. This is the chain rule. This is, again, you'd say, oh, well, Do I know how to differentiate cos 4x? No. But can I differentiate cos x? Yes. If I differentiate cos x, I get minus sine x. So again, you just act a bit ditzy and kind of forget about the 4x for a minute and get minus sine of 4x. Now, you multiply by the thing you pretended was x. I pretended this thing in here was x, so I differentiate that and I get 4. So the answer is just minus 4 sine 4x. And you're done. Okay? Let's say f of x is equal to tan cubed of 3x. How do I differentiate this? Well, remember, this is tan of 3x cubed. So first of all, we'll use the chain rule. The chain rule says, again, just pretend this was x, be a bit, kind of nonchalant and just say, okay, well, if it was x, what would I do? The 3 would come down. I do tan of 3x. I'd minus 1 off the power and get squared. Now, what did I pretend was x? I pretended tan 3x was x, and therefore I need to differentiate by tan 3x. Like so. So now, this is equal to 3 tan squared 3x. If I differentiate tan 3x, again, be a little bit ditzy and just say, okay, well, if I differentiate tan, what do I get? I get 1 over cos squared, or secant squared. So I'll keep it to 1 over cos. So it's 1 over cos squared 3x multiplied by, what did I pretend was x? I just forgot about this 3x for a second. I just pretended it was x and went from there. So I need to multiply by the derivative of that thing, which the derivative of 3x is simply 3. So this is just 9 tan squared 3x over cos squared 3x, like this. Okay? So that's it. Nothing more. Okay? Finally, if f of x was equal to the square root of sine x, how would you differentiate this? Again, this is sine x to the power of a half. So how do I differentiate this? It's just a half comes down, minus 1 off the power. And then you multiply by the derivative of what did you pretend was x? I pretended sine x was x. So you multiply by the derivative of sine x, which is cos x. So this is simply equal to cos x all over 2 square root of sine x. And that's it. Okay? All right. I think I'll just do one more of them, and then I might leave it there. If f of x was equal to cos to the 4 of 5x, how would you do this? Again, it's just cos of 5x to the power of 4. So f prime, again, if you pretend this thing was x, you would just do the power root, you'd say the 4 comes down, you'd minus 1 off the power, you get cos 5x to the power of 3. Now you need to multiply by the derivative, so d dx. Sorry, I made a little bit of a mistake. Okay, but basically you need to differentiate cos 5x. Guys, I'm really sorry. I never explained what this d dx was. Sorry, a df dx is the same thing as d dx f. Sorry, I never said that. I'm really sorry about that. That might have been confusing. Basically, d dx is just like differentiate f. So df dx is just the derivative of f. If I say d dx of f, I'm saying differentiate f. So all I'm saying here, I'm just saying differentiate this thing. Okay? Hopefully you picked up on that. If you didn't, I'm sorry about that. That was that was an oversight that shouldn't have happened. Okay. But I get 4 cos 5x cubed. Again, if this was just cos x, I just differentiate it, and what would I get? I get minus sine. So it's just minus sine of 5x. Again, multiplied by the derivative of the thing that I pretended was x. I pretended 5x was just x, so that's just 5 pops out. So I'm just left with minus 20 cos cubed 5x sine 5x. And that's that. Okay. All right. Now there's also inverse differentials. I'll just go over them quickly. Okay, they're not very important, but I'll just go over them anyways. So cos minus 1, so that's just inverse cos of x over a. d dx of it is equal to minus 1 over the square root of a squared minus x squared. d dx of sine minus 1 of x over a is simply equal to 1 over root a squared minus x squared. And d dx of 10 minus 1 of x over a is equal to a over a squared plus x squared. Like so. So basically, they might ask you, they might say, okay, well, y is equal to sine minus 1 of x over a. Basically, differentiate this. So what is dy dx? So how can I show that this is actually the case? Basically, what you always do is you just invert this thing. So you'd say, okay, well, that means that sine of y is equal to x over a. So x is equal to a sine y. So you just undo this. Okay, so you throw the sine to the left-hand side, it becomes sine y equals x over a. Multiply both sides by a, I get x equals a sine y. Great. Because I'm looking for dy dx, but I can simply calculate dx dy. Dx dy is simply a. If I differentiate sine y, what do I get? Cos y. Okay. So now, you can say that's fine. So dy dx is simply equal to 1 over a cos y. But now you might say, well, hold on. How am I going to figure out what the cos of y is? You're going to figure it out from this. If I draw out a triangle, a right angle triangle, it's saying the sine of y. So say this is the angle y. The sine of y is the opposite over the hypotenuse, so it's x over a. Using Pythagoras, you can show that this is equal to the square root of a squared minus x squared. If I ask you what the cos of y is, you would say the cos of y is simply going to be the adjacent, which is root a squared minus x squared all over a. If you plug that into here, the a's will cancel, and I'm simply left with 1 over the square root of a squared minus x squared. So that's how you'd work out the inverse differentials if you needed to. Okay, now they've never come up, so I won't dwell on it too long, and I wouldn't worry about it. But just in case it does, there it is. Okay. Now, the next thing that's important is the derivative of the exponential function. So we had e to the x, you would have seen before, ln x, these sort of things. Okay. Now, the derivative of e to the x is simply e to the x. So the derivative stays the same. d dx of e to the ax is equal to a e to the ax. This is just coming from the chain rule. It's like saying, oh, well, if I differentiate e to the ax, it just stays the same. Grand. But I need to multiply by the derivative of the thing that I pretended was x. I pretended this was x. And this thing, of course, is just a. So that's where this a is popping out. Okay? If you differentiate log, again, you'll never have to prove any of these. It's just you need to know that it is. If I differentiate the log, I get 1 over x. Or x to the minus 1. Okay? Very weird one, but it's just there. Okay? And if I differentiate a to the power of x, I get a to the x ln of a. Okay? So it's very similar to the e to the x. The only difference is that you just have a natural log here as well. Okay? So the thing is, e is 2 point, I think it's 718 ... whatever it is. But e is basically the number you need for the derivative of the function to still be the function. Okay. Now, obviously, if I differentiate 0, I get 0. But, it's the only non-zero function that if you differentiate it, you get back to the same thing. So that's what's so fantastic about the exponential, is that the y value that you get is actually just the slope as well. So if the y value is 10, the slope is 10. If the y value is 20, the slope is 20. And so on and so on. Okay. Which is quite interesting. Okay. I'll just do one example of each and then I'll leave it. If I wanted to get d dx of e to the 3x, this is simply 3 e to the 3x. So whatever number it is, you just bring it down. Okay? If I have natural log, ln of, say, sine x, and I want to differentiate this, again, if I just pretended this thing was x and got the natural log of x, what happens? It just goes 1 over that thing. So it's just 1 over sine x. Multiplied by the derivative of sine x, which is cos x. So that's it. Okay? Nothing more. And then if I differentiate, say d dx of 10 to the power of x, this is simply 10 to the power of x multiplied by the natural log of 10. So remember, this is 10 to the power of x times log to the base e of 10. Okay, just to be clear and transparent. Okay, I think that's it for this part of differential calculus. I'll go to the next chapter where we'll look at second derivatives, increasing and decreasing functions, kind of stationary points, stuff like that. And that'll be quite interesting. So I think I'll leave it there for now. I think this was probably a very long video already. So I think I'll leave it at that. Yeah, very long video. Okay, I think I'll leave it at that. So thank you very much for paying attention. And yeah, I'll see you in the next one.